Hello and welcome to another session where we are going to do an example by hand. We're actually going to do a couple of examples, and we are in what we call topic number 5, where we discuss effect size and power, or significance, I guess is the chapter heading when you look at the book, which we'll show in a second. And we're going to do what I call part B1, where in part A we have our little discussion and introduction. Then part B is where we work through a problem slowly and carefully. And then we'll also do a problem with the convenience of spreadsheets to give you some variety and some options. As always, the book we're looking at is the Statistics for Psychology book. We are going to be on page 223, looking at number 15, 16, and 24. Let's read number 15 together. In a planned study, there is a known population with a normal distribution. Mu is 0, sigma is 10. What is the predicted effect size D if the researchers predict that those given an experimental treatment have a mean of a variety of numbers? We'll do A and B. So we're doing 15A. Let's just write that down. 15A. Alrighty. So our effect size calculation, you can look at this number 6.1 for the effect size. It'll be the predicted or observed mean minus the stated one over the standard deviation. As usual, don't necessarily need a formula for that, but because it's a familiar calculation, but it is there in the formula sheet as a reminder anyway. So that's a very simple calculation, and we get negative 0.8. Now the negative doesn't really matter because it could be, let's say, extreme to one side or the other side of the mean, right? This one would indicate that it sits to the left, or not necessarily extreme, but positions relative to the mean. Rough classification of the effect size. I'll go to page 186 as a reminder of that little table, 6.2, where we classify approximately the different effect sizes to use words instead of numbers. And we got a size of 0.8, so that'll be classified as a large effect size. Again, the negative just indicates the direction. Let's also do B, just so we do more than one. And let me go back to page 223. Move it up a little bit here. We also have a predicted mean of -5. What is the effect size then? So we have our calculation, -5 minus the given distribution mean over the standard deviation. And then we, of course, get -5 over 10, which is -0.5, and that'll be classified as medium. The classification is just there for convenience. Sometimes it's right in the middle of the two, and then what do you say? It's just to have words where it's convenient and not just numbers, and then people have to think about, well, what do these numbers mean? Adding words to your findings is just much nicer for a reader. All right. So effect size, essentially giving a measure and classification of how far away I am from the mean, really. Let's do number 16 as well, which flips this around a little bit. Let's read this first. In a planned study, there is a known population with a normal distribution mu 17.5 and sigma 3.2. What is the predicted mean if the researcher predicts a, first, small positive effect size? So now we remember our, oopsie, my pen just fell. In number 16, let's move this up a touch. We think of our formula, which is effect size. I'll say here predicted mean minus distribution mean over sigma. But now I'm given the effect size and I'm looking for the predicted mean that would match that. So I have to shuffle these things around a little bit. I multiply both sides by sigma. Now let's show all the steps. So sigma times d will be mu predicted minus mu, or mu2, or whatever you think of in the formula. Let's go back to the book. And then I want to solve for mu predicted because that's the unknown. So it'll be mu plus sigma times d. And if you think about it, this looks very familiar to the similar direction of question when we worked with just z-scores and the normal distribution a couple of topics ago. So now I have my mu. Let's just make sure we have a 17.5 and a 3.2. So 17.5 here, 3.2 for sigma, effect size that they are hoping for or interested in. Firstly, a small positive effect size. So then when I look at the classification, that'll be 0.2. And I get an answer here. Let's go to our calculator. So we show something in the chat. We don't have much. Oopsie, let's just, where's my mouse? Where is my mouse? There's my mouse. So we'll calculate that. 17.5. You won't see what I'm typing until I finish typing it, but it's coming. Like so. 18.14. 18.14. That's not a very pretty 8, but there it is. So that is my predicted mean if I want, or I'm hoping for, a small effect size. So you see it's not far away from the 17.5. The effect size is just another way to relate how far away from the mean I am, really. Let me just check my spacing. I think we have enough space for the next one, which I want to do 24. So let's go there. That's on the next page here. 24, 24, 24 down below. It doesn't go into, yeah, it just stays on page 24. Let's just position it nicely. There we go. Okay, let's read it first, or at least most of it, and then we can go through it again and see what is this asking, what do we do here? This is the question on power. An organizational psychologist predicts that assembly workers will have a somewhat higher level of job satisfaction if they are given a new kind of incentive program. That is, he predicts a medium effect size. Now, this could come usually from a preliminary small study before they invest a lot into this proper study with a lot of people in general, in practice. You have a preliminary study, and that gives you your predicted effect size or predicted mean, we can go back and forth between those. And then you conduct the proper study, which usually costs a lot of money and things like that. So we have our prediction in terms of effect size, medium. On a standard job satisfaction scale, without the incentive program for assembly workers in this company overall, the distribution is normal, mu 82, sigma 7. The psychologist plans to provide the new incentive program to 25 randomly selected assembly workers. What is the power of the study? Sketch it, indicate stuff on your sketch. The explanation in part C, this book likes to explain everything in words, which is really good, but we're going to do it verbally and talk about it as we go. So I won't actually write out C. You can make notes from what I'm saying as we go and answer C that way. So let's just focus on the medium effect size here. Medium effect size means that my D is 0.5. Now we saw here how to go from D to my predicted mean. So that means that mu predicted is mu plus sigma times D. So I'm going to plug in, I'm just thinking about my spacing here. Whoops, no, wrong line. I need two diagrams here, so I think we'll be okay. So my mu, oopsie, is 82 sigma 7. Okay, so I have 82 plus 7 times 0.5. I'll do it, but I know you can do it in your head. I'll show it so we have something to see here. 82 plus 7 times 0.5, and we get 85. 85.5. Okay, so we'll keep that in mind. That is certainly an important step. So they might give me the predicted mean in another question. In this case, they give it to me in terms of effect size. If I have one, I have the other. So no problem there. So now power. Power is related to the type 2 error. Now, what is a type 2 error? A type 2 error is when I do not reject the null hypothesis, but I actually should have. I should have, but I don't reject it. So let's have a little diagram here. Actually, not a little one, but a diagram nonetheless. I'm just going to plan out my diagram here because for the power, we have one on top of the other. Oh, I want a little bit more bendy, normal distribution here. I always struggle with the symmetry. It's not great. Not that I'm a perfectionist, but I mean, sheesh, I want to be at least somewhat. Okay, we'll go with that. So we are testing our null hypothesis against this mean of 82. Standard deviation here. Remember, the distribution of means is what we're using because we have a sample larger than 1. So for the distribution of means, my comparison distribution has a sigma m that is going to be the standard deviation of the distribution of the individuals, the population distribution, over the square root, oopsie, there is my line, of the sample size, which is a very convenient 25, so 7 over 5. I guess we can do that as well. 7 over 5. Let me just show you the square root. Well, it doesn't really matter, right? You're not, maybe you're using MathBot. Maybe you are in my Discord and you want to use it. Then I'll use SQRT for square root 25 like so. and it gives me my 1.4, which is what we have to use in our calculations. 1.4, so remember that. So here our sigma m is what we're using, 1.4. Our mu is 82, like so, mu. Okay. So now how do we visualize what's happening in the hypothesis test? Do they give me an alpha? Yes, they are looking for an alpha of 1%. Okay, great. So let's indicate that over, let's just, because I know what's coming, let me just not run out of space and actually exaggerate this. I know it might not be as big of a tail, but I'm going to put it over there because I know what's coming. And if I put it very far, I'm going to run out of space on my page here. So that's the only reason. And it's just a rough sketch anyway. So I want to know what is the z-score that corresponds to these regions, 1% in the tail. Well, we're doing this one by hand, so we're going to go to our data tables here, statistical tables, and we're looking for the percentage in the tail of 1%. I don't have these memorized. I have to go look at them every time. I know it jumps back and forth a little bit. It's annoying. 1% in the tail. Now, in this case, just to mix it up, I know it's not exactly a 1 that we're getting. Most textbooks argue that, oh, well, the 0.99 is the closer, and then the more conservative, I guess, of the two numbers, pushing the tail a little bit smaller, so it's more difficult to reject the null hypothesis. Very little, but still. But in practice, we would not have these gaps. We would be precise, as we can be in the next example with spreadsheets. So we'll take 2.33 here. 2.33. Let me just check. That's on my screen. Good. I was worried that I'm writing something and it's actually not on the screen that's being recorded. And I just go about my merry way and no one can see what I do. Anyway, we're good there. So now we have to, let me just lift this up a touch. Actually, no, I want to see that. Now I have to think, well, what is the raw score that corresponds to this 2.33? I could have done it. Now, because of my tables, I go to a z-score simply to have one table, but this matches, of course, a specific raw score. How do I do that? Well, luckily, the formula that I see here at the top is exactly the same to calculate the raw score given the z-score. It's going to be my mean plus the standard deviation of the distribution times the z-score. And I'll squeeze it in here. Let's calculate it first, I suppose. We're calculating 82 plus 1.4 times 2.33. So this power calculation is a little bigger. Take your time here. Understand what you're doing. So we've done this before. Just calculate the corresponding z-score, the corresponding raw score from the z-score. So I get 262. All right. So now, what does this mean? This means that if I get an observed sample score, greater than this 85 point something, I'm going to reject the null hypothesis. Also, if I get an observed score less than this cutoff line, 85-ish, I'm not going to reject the null hypothesis. We want to investigate that scenario. Now, if my predicted mean is accurate, then the true distribution is not actually sitting here at 82. It's actually sitting at 85.5, which is slightly more than the observed score. So let's draw another distribution above this one, positioned at the actual, or my best guess for the actual mean, which is 85.5. So that's going to be a normal distribution. Same shape, but of course I'm not going to be able to draw it the same way. That seems very curvy. I don't like it. I know it's live and I'm recording, but at least I want a shape that looks somewhat similar. I do it a little bit so I can get the curvature somewhat decent, but of course it's a nice smooth curve, right? So that is now going to be centered in reality at the actual mean. The mean is not 82 anymore. The new incentive program has had an effect. We just don't know how big. Or probably a little effect. We don't know at all. Based on the predicted mean, it did have an effect. It did shift the mean to the right to a raw value of 85.5. So now, what does my 85.26 actually mean in reality? If I follow it all the way up, it sits over here, 85.262. Follow it all the way up. So now let's say this again. I am going to not reject the null hypothesis whenever I get a raw score left of 85.26. So my probability, my chances of that happening is based on the actual distribution, which is this top one, not the bottom one. This is different when I analyze or when I talk about the type 1 error, which is the probability of rejecting the null hypothesis when it should be rejected, right? Then I am looking at this distribution. The type 2 error is when the null hypothesis is true, I am on this bottom distribution. The null hypothesis assumes that there's no change. So 82 is actually the true mean still. So then this bottom distribution is perfect, and this 1% is my chance of a type 1 error, the chance of rejecting. But in the case where the null hypothesis is not true, this is not my distribution anymore. What is my actual distribution? Well, my best guess is it's centered at 85.5, and I need a preliminary study or something else to use. It's actually this top one. So the probability then needs to be analyzed using the top distribution. And the probability of me rejecting, the probability of me not rejecting the null hypothesis is this left area over here. So this is, let's say here, probability of type 2 error. Okay. Or we call it beta. Probability of type 2 error, alpha, beta. So now let's find out what is this probability. Well, before I can go to my tables, I need to standardize this 85.262 on this distribution. So the z-score here is the 85.262 minus the mean 85.5 over of course, sigma m, the standard deviation for this distribution, still the distribution of means, just centered more correctly. So 1.4. So let's see what we get. We're calculating. We are using brackets. 85.262 minus 85.5. Very slight, but it is there is a gap. Now I'm exaggerating it on my diagram, of course, so it's easier to work with. And we get negative 0.17. Negative 0.17. I didn't expect it to be huge because they're so close together, but I don't know exactly. So now we're going to look at our table, negative 0.17 for my z-score. Now let us find that first. Oops, not the book, the table, not the formulas, the table. 0.17. Now these z-scores are all positive. I'm looking for 0.17. 0.17 is over here. So now we can do one of two things, I suppose. I prefer to just look at the tail and say, yes, we're on the wrong side, but symmetry allows us to look at positive 0.17, which would be over here, and find that tail, and it'll be the same area. So I'll do that. Look at the percentage in the tail, 0.17, 43.25. And that's the same over here. So this is 43.25%. The power is just the rest of the, I'll do big little squiggles here. The rest of it, that is the power, which is going to be 100% minus beta if I'm working in percentages. Let's show that in the calculator. So that's very easy to do. 100 minus 43.25. And we get our 56.75 for the power. 56.75%. So whether I talk about power, whether I talk about type 2 error, they're interchangeable, really. All right. So again, let's go through the two errors. Type 1, the easy one, alpha. If the null hypothesis is true, I'm looking at the bottom distribution, then the probability of rejecting the null hypothesis is the probability of getting a score past this cutoff line on this distribution. That's the 1%, the alpha. And that'll be the wrong conclusion, right? Rejecting if it's actually true. If, however, the null hypothesis is not true, it's somewhere else, not centered at 82. It's over here. What would be the wrong conclusion then? The wrong conclusion would be still not accepting the null hypothesis. We don't accept, not rejecting the null hypothesis. When there has been a change, but I don't make that conclusion, I don't reject, that would be the incorrect conclusion. That is going to happen whenever I get anything less than 85.265 as a sample mean. But that's on this distribution. And there's a much higher, well, depends on what the predicted mean is. It depends on how much is shifted. That's a different probability that needs to be calculated on this distribution. That is beta, that is my type 2 error. And I can rephrase that in terms of the power. So the bigger the change, the bigger the effect of this incentive program, the more the top distribution is going to shift, in this case, to the right, the further to the right it is. And the further to the right it is, the smaller this left type 2 error area is going to be. So a larger effect corresponds to larger power. It is a stronger evidence, and that has a smaller type 2 error probability. All right, so a lot to think about here, but that is what it looks like for a typical power example. All right, until next time, where we will do another one, but with the help of spreadsheets. It's going to be tough to draw all this in a spreadsheet. We might still get a little drawing going to visualize what's happening here. Just the spreadsheets act as a glorified calculator for convenience. But that is for next time. I will see you then.